Dave even said he still thinks it's the waves, but I think this is a more exact and correct explanation than the waves. Because the waves, you never...
Yeah, I mean, all that stuff still can do it. The waves, the atmosphere, refraction, all that stuff can. This is just in perfect atmosphere, it would still happen. You would still lose your vision along that, whatever you're staring at, that horizon line, you're going to lose it.
Right, a completely flat, a completely no waves on a lake or something.
Yeah, you're still going to lose.
Right.
Oh, it's still going to happen, absolutely. But when you have waves, it literally can wipe out half of a city. The bottom half of a city.
Hundreds and hundreds of feet.
And you can't see those waves, right? Even when there's not waves, there's ocean swells. When there's little swells coming in, and when you're looking out far enough, because of the way that we see and everything ramps up, that swell will take out hundreds of feet of scenery on the flat level plain.
Right. So this, it's my bad drawing of a boat, but if you're observing the boat and you're this guy down here, let's say you're this tall or something, and let's say you're 6 foot tall, the boat's 40 foot tall. So if you think about what you're actually...
boat.
Huh? Yeah, no,
it's a nice boat.
I'm not a good drawer. What can I do? So if you're thinking about this guy who's looking here, and then he's looking here, but then you realize their eye line is actually here. So the way that we see things is it has to make a certain angle in our eye. And like Zach was just pointing out, that what'd you call this? The diffraction limit was in the middle, or what'd you call that line in the middle? Zach, what did you call it? I don't remember what you called it. Anyway, that line in the middle.
Sorry, I was muted. Yeah, that's your diffraction limit, they call it.
Okay.
That line across the center, and it will be all the way across from east to west. Now, if you had a square lens, there would also be a diffraction limit running north and south. Why it doesn't happen on a circular lens, I've never been able to find that answer, the up and down one. But if you have a rectilinear lens, which are very far and few between, there's cameras that most of them are pretty expensive, but those will have 2 diffraction lines running in a cross pattern across the center.
So people should recognize that these are angles, right? So that you can see that this is an angle here. There's a bad drawing of one, but you can see that angle and you can see the bottom one. Now, if we take this boat and move it this direction, so it's going away from us now, think about what happens as the boat moves, but if we keep these lines attached to the top and bottom of the boat, you're going to get a reduced angle for both locations, right? It's going to get smaller and smaller and smaller as this boat goes away. Well, eventually, the bottom part of the boat, the part from your eye line down, is going to reach that point that you no longer can see it. But the top angle from the top to your eye line still has enough angle that you can see it. In fact, it will always have more. It will always have more than the bottom, because you're always going to have more distance to the top of the boat than you would from your eye line to the bottom of the boat. So you're always going to lose the bottom half of ships first.
Yep. Even on a perfect day with no curve on a flat plane, you will lose it's not just going to shrink into a tiny dot to where you can't see any of it all at the same time. You're going to lose the bottom first, just due to the limitations of any type of, I was going to say your eye, but any type of camera, telescope, anything like that. Anything with a circular aperture.
Yeah, it all comes down to your angular resolution.
That's without any refraction whatsoever being involved.
Yes, all that just makes it worse. Any type of, even particulates in the atmosphere, moisture, anything like that will make it worse.
And that's why I like the Skunk Bay observations so much, is you can watch the bay, like the buildings and trees rise up and down, and you're keeping your camera in the exact same position, and yet, those...
Well, that's refraction, right?
Buildings and trees, they're going up and down. That island isn't sinking, but that's because of refraction.
Okay.
Yep.
Yeah. So,
and I have a test that people need to start applying to some of their long distance observations. If you have just doing a mirror flash, we need to get a blue and red light at the ends of each spectrum, and if there is refraction, the blue light will be lower than the red light, because blue light bends faster than the red light does due to refraction. So if they are still the same level, you can say, hey, they're the same level, this is not refraction causing this, why am I seeing this?